In this video, we're going to be taking a look at how to translate kinematic curves from one type of graph to the next. We have one example where we start with the position time graph and then move to the velocity and acceleration. One where we start in the middle with the velocity versus time graph and then produce the position and acceleration. And the last one, we have the acceleration versus time graph, and then we go backwards to get the velocity and the position. So for each one of these, I made them a three-part graph so that we could do three different types of motion within one problem. So let's call this section 1, section 2, and section 3. So here are details that I'm going to want to be paying attention to. For section 1, it's slanting backwards in the negative direction. So we have a negative velocity. And because my line is straight, it has a constant slope, which means it has a constant velocity, because the rate of change on a position versus time graph is the slope, and the rate of change of a position time graph is the velocity. So if it is a constant negative slope, then we have a constant negative velocity. Then for number 2, again, we're analyzing the slope, but if the position is staying constant, that means that we're not moving and the slope is 0. So we're exactly on the x-axis here on our velocity time graph to show that the object is at rest. Now for number 3, if you notice something is curved, that means that the slope is changing. If the slope is changing, that the rate that it's moving is changing, which means it's accelerating. The second thing you want to identify is if the curved line is getting steeper or more flat. So is it becoming more vertical or more flat? So this one is clearly becoming more vertical. So it's rising up, which means it's going in the positive direction, and it's becoming progressively more steep. So that means positive and getting progressively more steep, which means that it is increasing its positive velocity. So then this would be your section 1, 2, and 3. A straight constant negative slope for a constant negative velocity, no slope, no change in position, so the velocity is 0. And then we have an increasing positive velocity, so we have an increasing positive slant upwards on our position versus time graph. Now, every time you go from a velocity versus time graph to an acceleration versus time graph, that one is typically a little bit easier because, again, you just look at the slope, but there's not a whole lot to look at with these slopes because this is completely flat and this is completely flat. So section 1 and 2 have no acceleration at all. Now, that might seem confusing because these are very different. One is completely motionless, which is section 2, and then there's one part that's moving. But within each section, there's no change in velocity. This is a constant negative velocity, that the way that the person or thing is moving backwards stays constant, and then the way this thing moves, which is not at all, stays constant. So we have no acceleration for the first 2 sections, and then because there's a constant positive slope here, there is a constant positive acceleration for section 3. So when going from position to velocities to accelerations, you analyze the slope of the position versus time graph to get the velocity versus time graph, and then you analyze the slopes of the velocity versus time graphs to get to your acceleration versus time graphs. Now we're going to use all of those same ideas and apply the same concepts and skills to our second problem over here. So let's go from the velocity versus time graph to acceleration. So it looks like we have a constant negative slope all through the first 2 sections. Again, we'll call that section 1, 2, and 3. So if it's a constant negative slope, then we have a constant negative acceleration for sections 1 and 2. And then at the very end, we have no change in velocity, which means that we have 0 acceleration because the slope is 0. All right, now working backwards, this can be a little bit trickier. So what you want to do is either jot down some little notes or just kind of go through all of these ideas in your head. So here are the things that I go through. Number 1, this velocity is positive. It's positive because it's above the x-axis. Okay? And because the line is moving towards 0, that means it's slowing down. So something positive and slowing down means that it should be rising on the position time graph, but because it's slowing down, the slope should not get steeper. It should be becoming progressively more flat. So I'm going to rise up and become progressively more flat to show that it's slowing down. That's section 1. Okay, for number 2, this is a little tricky because this line is all continuous, so it seems like it's continuing the same type of motion, but now it's going from a positive velocity to a negative because it's dropping down below the x-axis. Okay, what that means is if I have negative velocities, that means I should be going lower and lower on my position versus time graph. Now, this isn't slowing down in the second position or the second section either, because you find out if things are going faster or slower based on whether they're moving towards the x-axis or away from it. So this one is moving from a positive number towards 0, and this is moving from 0 to, we'll say, -1, -2, -3, -4. So it's increasing its negative velocity. So I want to go down on the graph, and then I also want to get steeper and steeper and steeper. Okay, so it's going to look something like that. Okay, and then for section 3, I have a constant negative velocity. So whatever velocity I ended off with 2, I'm going to continue with that constant negative motion, and I'll actually end up sort of dropping off below this graph, but I'll sort of continue it on and then have a constant negative slope to show this constant negative velocity. So moving from this step to this step was definitely one of the more tricky ones. Okay, now for the last one, this is actually a very uncommon type of problem, but I'll just tell you the concepts and ideas that you would use to approach this type of problem. Now, the reason why this kind of problem isn't given very much is because this acceleration versus time graph is the least descriptive one as far as telling you which direction you're going and if you're speeding up or slowing down. Now, if you remember, we took a look at the slope on the velocity versus time graph to go over here to show that we had a constant negative acceleration. Now, this is a constant positive acceleration, which just means we have a constant positive slope. So that positive slope could look something like this. Okay, it could look something like this. It could look something like this. Those are all constant positive slopes, but they're different types of motion. This one's positive, this one goes negative and then positive, this one's all negative. Okay, that's why I said it's not very descriptive. So I'm just going to go with the original one and get rid of these previous two, and I'll show a constant positive slope for a constant positive acceleration. And then for this part, it is a constant negative acceleration, so constant negative slope, and then something with no slope at all. Okay, and then again, we'll call this section 1, 2, and 3, 1, 2, and 3. Okay, now this is the correct shape no matter which way you look at it, except this entire graph could be shifted upwards or shifted downwards. Now, going off the one that I drew, if I have a increasing positive velocity, then I'm going to want to rise up on the graph, and to show the increasing rate of movement, I'm going to make the slope steeper and steeper. So that's going to be section number 1. And then I'm not going backwards now, but I'm decreasing my positive velocity towards 0. So I'm going to rise up, but the slope is going to become more and more flat because the rate that it's moving upwards is getting smaller and smaller than actually hitting 0. When it hits 0 completely, then that means you're remaining at exactly the same position because you are at rest. Okay, so with those 3 different examples, I hope that's helpful to you in analyzing different graphs and being able to create graphs starting with position, velocity, or acceleration. Thank you very much for watching and listening.